So today we're going to talk about nuclear magnetic resonance. And the word nuclear is maybe a bit charged, like radioactive, nuclear power and stuff like that, but it means related to nuclei of atoms. Okay, so there's nothing radioactive. So that's good. Magnetic, so we're going to use large and strong magnets. And nuclei are also small magnets. Not all of them, but some of them. Okay, in resonance, what does resonance mean? It's a very fancy way to say absorption. So we already talked about light absorption in UV vis. We talked about absorption of other kinds of radiation like infrared. And so NMR is basically an absorption technique, but they don't call it absorption, they call it resonance, just to confuse you. Okay, so we know if we look at an atom, we have the nucleus, right? And what's in the nucleus? Protons, yes. What else? Neutrons, yes, also good. So we have protons and neutrons, right? And then around it, we have electrons. Oops, it's here. Okay, so we know this. Just by the way, NMR is the most important spectroscopy in chemistry, basically. Scopy, let's say in organic chemistry for now. Chemistry. And why is it so important? Because it's very predictive. Remember in infrared, I said you have all these infrared things and modes and things, and we don't know what it means, and it's difficult. In NMR, everything is super well defined, and you can basically solve a molecular structure based only on NMR or maybe a few things together. Okay, so if the nucleus, so this thing is the nucleus, right? So if the nucleus has, one S, of course, has an odd mass, odd, like not strange, but you have even and uneven. So even and odd. Odd is, 1, 3, 5, 7. An odd mass, and or an odd atomic number. Okay. If you have either of those, then the nucleus has a quantized spin angular momentum, and it will have a magnetic moment. Okay, so that's important to know. So let's look at a couple elements. So we're going to make a table. Actually, okay, let's do it. So what's the most commonly looked at element or atom in NMR? Hydrogen, yes. So we're going to look at, we have to distinguish the different isotopes, right? So the most abundant element, which is hydrogen, we're going to call it a proton, right? Because we're talking about the nucleus. Then we have the other isotope of hydrogen, which is deuterium. And there's also tritium, but it's very, very rare, so we don't care at the moment. And then I'm writing carbon, nitrogen, fluor, and phosphorus. Okay. Let's draw this table. Okay, so the first thing is I'm going to list I, which is the nuclear spin quantum number. And then this is the number of spin states. I'm going to explain what that all means. And the natural abundance in percent. So natural abundance means how frequently it's found in nature, right? So for the proton, we are lucky because the natural abundance is 99.98%. So most hydrogens you see in nature are 1H, they're protons. And their spin quantum number is half. And therefore the number of spin states is 2, because there's a very easy little equation. So the number of spin states is 2 times I plus 1. So if the spin state is half, which is the most common, as we'll see for the NMR we're going to talk about, it's 2 times half plus 1 is 2, okay? So you'll see that most of the ones, except for deuterium, this has a nuclear spin quantum number of 1. Therefore, it has 3 spin states. The abundance is 0.015. Okay, so it's rare, or more rare than normal. Okay, the other ones are all half. It's easy. So all spin states too. We'll get back to what spin states are just in a second. Okay, let's finish this up. So carbon 13, 1.1%. So the other is mostly carbon 12. And when people talk about carbon dating and bones of dinosaurs and stuff, they are looking at carbon 13 because that actually degrades over time. Nitrogen 15, 0.36%. And then for fluorine and for phosphorus, we're lucky because the NMR active isotope is 100% abundant. Yes?
I want to ask about the tritium. Why are we ignoring it here?
Because it's very, very, very rare. So
it's still very useful in science. So
yeah, it's useful in science, but not so much in NMR. Also, the price would be quite high. I mean, you can buy deuterated water, D2O, for NMR. It's already quite expensive. I don't know what tritiated water would cost, but I'm guessing very, a lot. Okay, so we'll get back to these spin states, but the other ingredient we have is a magnetic field. Magnetic field that we're going to call B0, okay, B0, with units Tesla, T. So anyone has an idea, if you have like a fridge magnet, that you have in your kitchen, what's the strength of a fridge magnet? Anyone has an idea? Yes.
I would say less than 1 micro Tesla.
No, micro Tesla, you're talking about the Earth magnetic field.
Oh, okay.
Yeah. So a fridge magnet would be 50 millitesla. If you have really, really strong magnets, like we have this neodymium boron iron magnets in our lab, you can go to 1 Tesla. Anything higher than 1 or 2 Tesla, you need a superconducting magnet, which is very expensive. We're going to talk in the next class about, how the NMR machine looks like, but this class will be just about concepts, okay? So without a magnetic field, all the spin states have the same energy. Okay, and so in NMR, they call that degenerate. Don't ask me why, but it's a very fancy word for saying it's all the same. And so when we apply the magnetic field, so with B naught, then the energy levels, they split. Because the nucleus has a magnetic moment, mu. So the nucleus itself is like a tiny little magnet. And if you put it in a big magnet, then it will do something interesting. Okay, what is this something interesting? So let's imagine we have the magnetic field in this direction. Magnetic field is a vector, right? It has a direction and it has a magnitude. It's a vector. And I'm going to draw a spin, and I'm going to use my little library. Okay, so a lot of times in textbooks, you will see a spin something like this. So it's a little ball that rotates around. It does like the right-hand rule, right? So if it rotates counterclockwise, the spin is up. And if it rotates the other direction, spin down. So this is spin up, or spin plus half, right? And then if we take the same thing, and I'm just lazy, right? So I'm just going to do like this. There you go, spin down. Oh, actually, this is not, okay. Doesn't turn in the right direction now. But okay, this is spin minus half. Okay? So what happens now when we look at the energy levels? Okay, energy. I'm going to plot energy versus the magnetic field strength B naught. So when we're at 0 Tesla, okay, this is in Tesla, right? When we're at 0, I just said that this plus half or minus half, they're at the same energy level. And when you increase the magnetic field, those energy levels increase. Okay, so you get splitting of the energy levels. And let's say we make 2 new energy levels. And so the higher energy will be minus half, and the other one will be plus half. Any idea why? Why is minus half higher in energy? Because if you look at this little magnet, it's pointing down and the field is pointing up. So that's energetically less favorable than when the field is the same, right? If you have a small magnet and you put it in a magnetic field, it wants to align with the magnetic field. Okay? So this energy difference, delta E, is, like in all the other things we talked about, Planck times nu times a frequency. Right? So let's write that again. Delta E is h nu. And so this is frequency. And we're going to write it like this. Planck over 2 pi times B naught. Okay. And so this gamma is, they call it the magnetogyric ratio. Sometimes also the gyromagnetic ratio. It's the same thing. And this is the magnetic field, right? Field. And so what we can do from here is we can write out frequency, nu. I'm just rearranging this equation, right? Times B naught, okay? And if we plug in some numbers for a proton, so this gyromagnetic ratio for protons is 267. This you can just look up in the textbook. Over 2 pi times, let's say we use 1 Tesla, which is not super strong, but okay. It's a magnetic field. And then it would say 42.6 megahertz. Okay, so that's for protons, right? So if you think about it as kind of equivalent to UV vis, then you want the radiation that you use to excite the atom has to match this energy level. Remember, we talked about that in UV vis and in infrared, right? So in NMR, it's basically the same thing. So very similar to infrared and UV vis, we're going to use this Boltzmann ratio to calculate the population of the spin states. Yes.
The magnetogeric ratio, what does it represent physically in our work? Like, is it a vector?
Yeah, it's I kind of skipped over that because I didn't find it so important, but it's a scalar. It's the ratio of the spin angular momentum and the magnetic moment. I think I have to look it up exactly. It's a constant. So if you have, let's say, protons, then it's 267.
You just have to learn it like that.
Well, you have to just look in a table and look it up. It's a constant. You cannot really do anything. In the next class, I'll put tables with all these values. Okay, so we're going to use this Boltzmann distribution. So the number of spins that are minus half over the number of spins that are plus half is, and this is the same as we've seen already 3 times, minus delta E over KT, or E to the power minus Planck nu over KT. Okay, so Planck, you know this, 6.624 10 to the minus 34 joule times second. Boltzmann constant, 1.38 10 to the minus 23 joule per Kelvin per mole. Temperature, let's say room temperature, 298 Kelvin. And nu, we're going to take 60 megahertz. That's like an old NMR machine. So in NMR machines, they will express like what kind of machine is it? Then they say, oh, it's a 60 megahertz or a 200 megahertz or a 500 megahertz. Okay, and we'll come back to that. But let's say we plug in these numbers and we calculate this ratio. Okay, then it will be, if we have 1 million spins down, we will have 1,000,009 spins up. So it's a tiny difference, right? So imagine you have a solution with many atoms and they are floating around. You put the magnetic field on, the energy is split, and there's this tiny energy difference. So most will be, up, but almost equally they will be down. Okay, so this tiny little number here is called the excess population of spins. Okay. So if we look at the frequency of the NMR machine and we look at the excess population, right, this is dimensionless, and the magnetic field of the machine in Tesla, so this is B naught. Okay. So we have 60 megahertz, 100, 200, 300, 600. So the most powerful NMRs nowadays, they are 900 megahertz. There's even gigahertz NMRs now. They are very expensive. Okay, so the excess population increases with the magnetic field of the NMR. Okay, so here, 60 megahertz, we have 1.41 Tesla, 2.35, 4.7, 7.05, 14.1. Okay, these are already seriously high magnetic fields. And the excess population increases is just plugging in this equation, 32, 48, 96. So this means that a stronger NMR machine, right? So that means higher magnetic field and therefore, for higher frequency. Has also a higher excess population. So that means more NMR signal. So that's why people have been trying to get stronger and stronger and stronger magnets, because you get more NMR signal. And as you will see later, the chemical shift is also more resolved. Okay, now we have to go into something strange, which is called precession. Precession. Okay, what is that? So I'm going to pull back my little thing here. Okay, so when you put your nucleus in the magnetic field, the energy is split, but it does something else. It does a precession, which is a kind of elliptical motion around its axis like that. Okay. Right, so this is like when you have this kids game. I don't know what it's called in French. What's this game? You have a little thing you spin around and it goes around. Okay, that thing. So when it's going around, it will turn, right? It will turn, but it will also, the axis will also slowly rotate. The Earth also does this, right? The Earth, we are on planet Earth, right? Still, guys, hi. Okay, so the Earth is turning, but it's also precessing. You know this, right? That's why we have seasons and stuff. Okay, so you have this precession of the spin as well. And the frequency at which this precession occurs, right? So this thing is, let me just draw some arrows on this. All right, so this thing is going around. And the precession frequency, this here, which is omega, it's called the Larmor frequency, omega. Okay. And so it will do that in a magnetic field. And so for protons, at B naught is 1.41 Tesla. This Larmor frequency is 60 megahertz. Okay, and so the magnetic field here is here, and this thing is 60 megahertz. Okay. Okay. So let's now try to understand how we get an NMR signal, right? So this, we're going to call this the magnetic resonance process. or as I said before, absorption. Okay, when do we get absorption? In UV vis or in infrared, when the energy of the frequency that you use to excite is the same as the energy that you're absorbing, right? So in our case, we have some new, I'm going to call it RF, because we use radio frequencies. We'll get back to that. We're not using light, we're using radio frequencies, is Planck times omega, right? That's one of the conditions to get resonance or to get absorption. Okay, I'm going to copy this thing. There we go. Okay. So we're going to come with a radio frequency signal here. Radio frequency here, which has energy h nu RF, and we're going to use 60 megahertz. Okay. And what happens is you get a kind of absorption process, but this absorption, the spin of plus half flips to minus half. Okay. So that's step number one. Let's call it steps in the process. One is a short radio frequency pulse is used to achieve resonance with all nuclei, let's say in the molecule, at the same time. Okay, so the pulse looks something like this. So I have intensity here and I have time here. And it will really be something square like this, right? Up. Okay, and this pulse duration is typically 1 to 10 microseconds. And now to confuse you, I don't know, I'm not going to explain all the physics behind this. In the actual machine, they don't use the resonance frequency of the protons, but they use a higher frequency. So we're going to use 90 megahertz, which is not resonant, so it's weird. But if you do a 90 megahertz pulse very, very shortly, then actually the system doesn't have time to, get resonance with the entire frequency. So this pulse, and this is because of the Heisenberg uncertainty principle, that basically means, I'm just going to show you the results. So the intensity versus frequency that you actually get, nu in megahertz, will be something like a distribution. So instead of getting one frequency, so if I would leave the intensity on for a very long time at 60 megahertz, then I would just get 60 megahertz very sharp, which is nice. But I want to hit all the nuclei, which are going to have slightly different resonance frequencies, because it depends on the local environment of each nucleus. Okay, so I use 90 megahertz, short pulse, which effectively excites all the nuclei. Okay. So after those spins are flipped, they have to return, they have to relax, right? So step 2 is after the radio frequency pulse, the spins relax while emitting different frequencies of radiation that depend on their environment. Okay. And so this emission is called free induction decay, or FID. Or some other people call it the time domain signal. Okay. So what does it look like? Okay. So we have here some detected emission versus time. Okay. And we'll get something like this. Okay. So it's a signal that has two components. It has basically a decay, like an exponential decay. The signal is decaying. Plus it has some kind of sine, a signal, which is basically a bunch of sine, cosine waves. Okay, and just like in infrared, we already talked about the Fourier transform. So it's going to come back here. See, frequency. And in NMR, the units are ppm. I'm going to explain why. It's very strange. But we're going to transform the time domain to the frequency domain. So this will basically give you some noise, and then a signal, and then more noise, right? So let's say this is at 2.1 ppm. Okay, so we have done Fourier transform to get this signal to give you a peak in the frequency domain. Okay. So every measurement on NMR, and in NMR that's called a scan. So every scan records an FID, free induction decay, and the signal to noise ratio. So this is the intensity of the signal, and this is the intensity of the noise. So this S over N can be improved by doing more scans. And it goes with this scaling. So signal to noise scales with the square root of the number of scans n, small n, right? So if you take more scans, your signal becomes larger. Because noise is random, your signal is not random. So if you do many experiments, your signal to noise ratio is better. It's kind of generally true for many spectroscopies, but here definitely. Okay. How are we doing so far? Everyone is still following? There's a question.
Yes, I wanted to ask from earlier, you wrote down this emission is called pre-induction decay FID, or earlier you said that they short radio frequency causes used to and then adhere resonance with all nuclei, right? But
achieve. Achieve, sorry.
Oh, it's here, sorry.
Yeah, I'm writing a bit. The notes I will put online, they are going to be.
I've read that, so.
Yeah, sure. But I will put the nicely written with colors, things that I do nicely. I will put them online. Achieve, yeah, achieve. Other questions so far? No, okay. So how to understand the fundamentals? Okay. So we go back to our fields, right? We have B naught here, and we have our spin. Yeah, so the first drawing that I used was this one, right? Spin, it's here. So this would be one spin. We can draw this in a different way, okay? And I'm going to just steal this axis here. Okay, so this is a XYZ axis, right? Three-dimensional frame, easy. So if I draw this spin in the what's called laboratory frame of reference, I can draw it something like this, right? So here, the spins, so I'm going to put little accents. The spins are precessing, right? So I'm going to, same thing here. The spin is precessing like that in the laboratory frame. Laboratory frame means like the real world. We are living in the laboratory frame, right? We are observers and something is moving. Okay? So now we can think of that. So that's one single spin. Now if we take many spins, okay, I'm going to copy this. Okay, so now if there are many spins, there will be some spins up and some spins down, right? We already said that. So, okay, there will be some down and some will be up. And there will be more up than down, right? Because of the energy difference. Okay, let's say we have 3 down and 5 up, something like that. So these are the spin plus half, and these are the spins minus half. And they're precessing, right? They're going around like this. Okay. So how can we think about that in a relative frame of Strasbourg? So if you go to Place Gutenberg, you know Place Gutenberg, yes. There's a very nice carousel, right? So let's imagine we are going to the carousel. This is a very crappy carousel, but okay. I'm going to make it nicer because I have horses. Okay, this is a horse, right? And this is some person. So this is the observer. This is a horse. Okay, the carousel is turning, right? Carousel is turning around and the observer is looking at the horse. So what does the horse do? It moves, right? So if you stand next to the carousel, the horse will go around and you will see a moving horse. Okay, nice. Now what happens if you step onto the carousel yourself? Okay, so now second scenario. I have my little observer. And the observer is now standing on the carousel as looking at the horse. What happens now? Nothing. The horse is standing still, right? So this is the laboratory frame of reference. And this, we would call it the rotating frame of reference. Okay, so that's nice. So we're going to compare these two to each other. Okay, so let's draw now the axis back, right? So I'm going to compare again this thing, which was our lab frame. I'll put it under the horse so you see actually what the difference is. Okay, so right side, we have the laboratory frame of reference. We have spins up, we have spins down. They're precessing, it's all going crazy. And we have now a rotating frame of reference. Okay, so now you have to imagine that these axes are rotating around the z-axis at the same speed as the precession of the spins, right? So you see these accents here, that means lab frame. And no accent means rotating frame. So how can I now, with one arrow, indicate this situation in the rotating frame of reference? Well, it's easy. I just have one arrow, which is the bulk magnetization. So if I take the sum of all these spins and we calculate it with Boltzmann, that there are more spins up than there are down. So, and they're radially distributed. So if we sum them up, we effectively have one magnetization that is up. Question?
Yeah, my question would be, if we're using the carousel as an example, wouldn't the rod that's holding the horse also be rotating around us? So if the observer is looking at the rod, it would also see this rod moving in a circle.
Yes, but if you're on the so if in the case the observer is on the carousel, this rod is also not moving.
All right.
Right, so it doesn't really matter if it's the horse or the rod. Okay, let's assume the horse is also not spinning on the rod, because our life is already more difficult than it needs to be. So okay, so it's very important that you understand. Are you all seeing how we go from here to here? So if all these spins are precessing, let's say at the same speed. More spins are up than down. They are radially distributed. So if I take the sum of all these arrows, I will get this big arrow, which is called, so M naught is a vector that shows what's called the bulk magnetization of all spins together. Okay. This is okay, you're following, it's good. It's going to get a little bit more complicated, but not much. Okay, so now assuming this rotating frame of reference, we're going to go back to all these processes that are happening. So we're going to have the pulse. And the pulse is going to flip this magnetization. And so what we're going to do is I'm going to draw again these frames of reference. Okay, so left is still rotating frame. Right is laboratory frame, right? Which means accents. Okay, so if we give this magnetization a pulse, okay, it's going to flip. Sorry. Okay, so it's moving from the z-axis here down with this angle theta. Okay, so this is still, I'm still comparing, right? This is the lab frame, rotating frame. So in the lab frame, it's a bit more difficult. I have to draw all these things again. Okay, so in the lab frame, just to know what's going on, we basically have all the arrows in one side. So all the spins, they are pushed to one side of this circle, so they are no longer radially distributed. So if I take again the sum of all these spins, then I get this big arrow M0 in the rotating frame. So that's after the pulse, right? The pulse was this short radio frequency thing versus time. Okay. So this is 90 degrees, right? So this is called a 90-degree pulse. Flips the magnetization. Not into the XY plane. Why is that? So Z is the direction of the static magnetic field, B naught. But the radio frequency pulse comes from the side, in the XY plane, and also the detection happens from the side. So only magnetization that is in the XY plane can be detected. Okay. And this pulse angle theta can be anything, right? It can be 45 degrees, it can be 23 degrees, it can be 180 degrees, etc., etc. Okay. And only magnetization in the XY plane can be measured. Everything along Z or minus Z, doesn't matter, is what's called NMR silent. Okay, so you have this bulk magnetization, you come with the radio frequency pulse, boom, the magnetization flips in the XY plane, and then it has to relax. Okay, so part 2, spin relaxation. Okay, I'm just taking back these 2 points we were discussing about before. Okay, so there are 2 pathways. 2 pathways to spin relaxation. And they're called, oops, T1 and T2. Very original. Okay, so starting with T1 relaxation. Okay, we have to draw a couple of these things. Ooh, that is a bit, okay. Okay, so we start with our magnetization along the plus y-axis, right? So this is M0. We're now in the rotating frame of reference, which is easier to understand. And we're going to draw this thing here. Okay, just need to copy this also. Okay. So this spin, oh, sorry, the magnetization is going to travel along this arc back to the z-axis. Why? Because with the spin or the bulk magnetization up is the equilibrium. Right? We just calculated with this Boltzmann ratio that we have more spins up than down. So the bulk magnetization has to be along B0, right? Which is the static magnetic field. Okay, so M naught is going here. And it's doing that with a pseudo first order rate. So we have d m dz dt. So that's the real, actual magnetization along z versus time is the magnitude of m naught minus mz over some kind of constant, which is t1. So t1 is actually a time. So if we solve this, this is an ordinary differential equation. We solve it, and we get this, minus e to the power minus t over t1. Okay? So graphically, what will happen? So I'm going to plot time in time over t1, right? So I'm going to just normalize by t1. And here I'm going to put the magnetization along z over m0. So I will get not a straight line. I have to curve it. Okay. So I'll get a straight line, something like this. Okay, where this level, of course, ends at 1. And here, okay, a little bit more. Let's say here, 2. I'm already at 85% relaxed. And let's say here, I'm at 5. So if you wait 5 times t1, which is a constant in seconds, then your magnetization is fully relaxed to the thermal equilibrium position. Okay, so T1 is a time. And for protons, it's like 0.5 to 5 seconds. And it is about 2 to 30 seconds for carbon 13. Okay. That's T1 relaxation. Now there's another one, which is called T2. And in a bit, we'll understand why these things are important. So T2 relaxation, I'm going to copy one of these guys here. Copy. Okay. Let me just. Okay. Yes.
Is the MZ over M5 for the axis or for the text on the left?
Sorry. This.
No. The MZ over M5.
Oh yeah, sorry. That's the axis.
Oh,
Okay.
okay.
That's sorry again. I'm writing a bit too fast and a bit sloppy. Okay. So what happens now? It's a bit easier to understand in the rotate or in the laboratory frame of reference. Weirdly, okay. So I'm going to draw. So look carefully what this is, right? So what I'm doing is I'm taking the XY plane, right? And I'm plotting it on the side, but in the laboratory frame of reference, right? We have here lab frame. So if we have this situation here, it's like you have a bunch of spins that are grouped together pointing along the y-axis. But now we talked about precession. And so the precession frequency, if we go back, let's go back. Okay. So the precession frequency, okay, I didn't write that. That's pretty stupid. Okay, but the precession frequency depends on the magnetic field. You can see it here, right? So if this is for proton, right? So this is the precession frequency at 1.4 Tesla. At 7 Tesla, the precession frequency is 300, which means it's precessing faster, right? So you can imagine that if I have my NMR machine and I have my magnetization pointing in the y direction, I have a bunch of spins, but the magnetic field will not be exactly perfect, right? So the spins don't experience exactly the same magnetic field B naught. And there are two reasons. Okay. One is, so these are reasons. One is imperfections in the NMR machine. So that's called T2 delta B naught. So this means you have a variation in the magnetic field, and this is associated with a certain relaxation time T2. And as we'll see in the next class, in the machine, you have special small coils, which are called shimming coils. So when you go to an NMR, which you will do later in the 3rd year or in your master, you need to shim the magnetic fields. So users are shimming. No. To improve the uniformity of B naught. Okay. The other reason, and then I'll come back to the drawings, is that the nuclei produce small but local magnetic fields. Okay. Which we'll call T2. Okay, let's get back to this. So we have the pulse, which kicks the magnetization into the along the y-axis. So in the lab frame of reference, that's a bunch of spins pointing in this y-axis direction. And I need 4 more of these. Okay. So every time I'm taking the XY plane, and what happens is that, let's say this spin, this spin is experiencing a slightly higher magnetic field. Now B naught is a tiny little bit greater. So it precesses faster, it rotates faster. And maybe this spin has B0 a tiny bit lower. Okay. So what happens over time is that the spins, they will start to fan out over the whole radius. Right. So after some time, so this is versus time. Okay. Time. Okay, I have my spins, and they will start to just move in all directions. And after a very long time, I basically have all the spins that are uniformly distributed, and they're just pointing in all directions equally. So the total magnetization of this radial spins is 0. Right, so if I draw in the rotating frame, it just looks like this arrow is getting shorter. Right, so M0, M0, and here it's completely gone. Right, so T1 relaxation is M0 moves back to the Z-axis, and T2 relaxation means it's the fading out of all the spins in the radial plane, which makes them undetectable because they're uniformly distributed. Okay, and now you think, like, who cares about all this T1, T2 stuff? Okay, so the importance, so if we take these 2 contributions, right? So this is the machine, and this is, let's call it a real contribution. We can calculate an effective T1, which we're going to call T1 or T2 star, is the sum of T2 plus 1 over T2 delta B naught, right? So this is the real T2 relaxation, and this is imperfections in the machine. And if you look at an NMR peak, it has a Lorentzian shape. Okay, that's a pretty ugly one, but okay, it has a sharp point. It's not a Gaussian, it's Lorentzian. And okay, let me draw this again because it's really ugly. I think I even have, look, yesterday I was spending a lot of time to draw a nice one. There you go. So it's a Lorentzian, and the width of this peak at the half height so the line width, delta nu, right, is 1 over pi times T2 star. So if your magnetic field in your machine is not very homogeneous because you didn't shim it well, that's something you have to do. Now it's automatic, it's auto shim. But in my glory days as a PhD student, you had to do it by hand. And you can actually see that the peaks are very wide if you don't shim well. And also they can get weird shapes, okay? We might get back to that in the next class. But so it's an important practical thing to do. So for spin half nuclei, which are basically all the ones we're going to talk about in this class, the main contribution is this T2 delta B naught. Main contribution. So that means your machine is not good, or you didn't use the shimming coils well enough to get a very constant magnetic field. But for spin larger than half nuclei, they also exist. You can get significant T2 can lead to broad lines. So chemical shift and shielding. Okay. So not all protons, so 1H, right, have exactly the same resonance frequency. And that's because they are what's called shielded by the local electrons around them. Okay. And so B0, the magnetic field, induces a local magnetic field that is in the opposite direction. And that's called diamagnetic shielding. Sorry, NMR has a lot of fancy words and jargon, but okay. So if you have an environment in your molecule that has greater electron density, that means it's more shielded. That means it will precess at lower frequency. Okay. Let's put some chemical examples because it's way easier to understand. So if we have chloromethane versus fluoromethane. Okay. So we're going to look at the, sorry, should have made this red. Okay, so if we look at the frequencies, difference in proton frequencies is 72 hertz. Okay, which is not a lot because the NMR has 60 megahertz, right? So the difference is 60 million 72 over 60 million, which is, if you use fractions or percent or even per mil, it doesn't make much sense because the differences are tiny. So they express that in parts per million. Or ppm. So the x-axis in an NMR spectrum doesn't have hertz or megahertz, it has ppm. Okay, weird. We're going to get into more detail, but you see that the differences are very small. So small that it's not accurate to determine absolute frequencies. So in an NMR, it's very difficult to put an unknown atom or compound and measure the absolute value of the frequency of your compound. It's not accurate enough because the differences are so small. So what do we do is we compare it. Signals are compared to a reference compound. So always when you do NMR, you have to put a reference compound in your sample. And the one that is basically always used is this one. So it's a silicon with 4 carbons with protons. Okay, so it's TMS, tetramethyl silane, right? CH3 4 times silicon. Okay, and so these protons, they are very shielded, as it's called. Are very shielded. And by definition, it is set to 0 ppm. Okay, so when you add, for example, you have your molecule, you add deuterated chloroform, it will have a trace of TMS in the bottle, and in your NMR, that's 0, and in the software, you can set it to 0. Okay, so what is the definition of chemical shift? So it's delta, and the units are ppms, because it's a difference, but it's also a normalized difference. So delta is the shift of your signal versus that of TMS, which is set at 0 in hertz, divided by the NMR spectrometer frequency in megahertz. Oops, megahertz. Right, and that's ppm. So you measure the difference versus the protons of TMS, which are very shielded, and they are in a region which typically doesn't overlap with your compounds. And then you divide it by the NMR spectrometer frequency. So for example, if I take bromomethane, the shift is 162 hertz on a 60 megahertz NMR machine. but the shift will be 270 hertz on a 100 megahertz machine. But the chemical shift will be the same, because if I take 162 hertz over 60 megahertz, and I compare it to 270 over 100, it's the same, it's 2.7 ppm. Right, so the reason why we use ppms is because there are many different NMR machines, they all have different frequencies, so if we would use frequency, we would go crazy, right? So chemical shift is uniform on all the NMR machines. And the axis, oops, no, I'm not here. Axis, I have an axis here. Right, so the scale in NMR has the 0 on the right side, which is TMS, right here. And then it goes in the opposite direction. So it counts up to the left, strangely, but okay, welcome to NMR. So that's the scale on the x-axis. And there's no y-axis on NMR. The y-axis means nothing, because it depends on how many scans you do and on the pulse power and on a lot of things. So the y-axis doesn't exist in NMR. Okay. We're getting to the more interesting part. Chemical equivalence. It's a very fancy way of saying all the protons are equal. Protons that are in identical chemical environments have the same chemical shift. Okay, so let's draw a couple compounds. And then we'll do a mini quick quiz. I'm going to draw the protons in red. It's easier to see. Okay. So for these compounds, how many different NMR signals do you expect? What do you think?
On the same term or separate?
All these compounds are similar. What do you see in these compounds?
The symmetry.
Yeah, they're symmetric, right?
So all the ash has the same environment.
Yeah, so all the protons see the same environment because there's symmetry. You know, there's C6, C5, and C2 symmetry. So all these protons see the same chemical environment. Therefore, in this case, all the protons are equivalent. So you will only see one chemical shift. Okay, that was easy. Let's go to this compound. Okay, I'll do it kind of like this. Proton, 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 proton. What do you think here?
How many peaks?
Yeah, how many different chemical shifts do you expect? Is there symmetry?
No.
No. So these ones are kind of the same, right? Because they're on the same methyl, and these ones also. So I have two environments, exactly. So I have this one and this one. Okay, let's do another one. What about this? Yes, right? So these ones all see the same environment. So this would be environment 1, and these ones are in the same environment. Okay. What about, so this one is 2 different. Yes. Let's do one more and then we see if you guys understood it. Okay, the trend is kind of becoming a bit too obvious now, but okay. So which ones?
The first ones, H4.
Yeah.
The H2. And the H2.
Yeah, you're right. Okay. Yeah, it was 1, 2, 3, you know. I should have put 4 just to confuse you. Okay, we're almost going to end, but so, okay, now we have these different chemical environments that give different chemical shifts, right? So let's put, again, I need my axis. There we go. I'm going to draw an NMR spectrum. Oops, not this one, sorry. So I have a peak here. I have a peak here. And I have a peak here. Okay, and I have TMS here, right? That's my reference compound. Okay, so I'm going to give you the molecule. Yeah.
Can you just tell me again why we don't see a, how can I say, a peak like a real peak, not
Why do we see a peak?
no, a peak, yeah, a straight line, not
Not, okay. So not a Gaussian, you mean?
yeah.
So NMR peak shapes are Lorentzian. Don't ask me why. That's a good question. I will try to look it up. But
I think a small difference between each peak.
yeah,
So normally the peak should be very
narrow.
yeah.
Yeah. So in NMR, the peaks generally are quite narrow, except if you go to polymers or proteins or something, big molecules, the peaks become very broad, and then it becomes kind of difficult to see anything. But a small molecule in a good solvent, the peaks will be sharp because the T2 relaxation is long, so it doesn't really matter. Yeah, other question.
Yeah, this may be a stupid question, but what symbol do you use for ppm? What is it called?
The symbol for what?
ppm, part per million.
Oh, it's so the so chemical shift is delta.
Oh, this is a small delta.
Yeah, it's a small delta. Sorry. Chemical shift is delta, and ppm are the units, parts per million. Okay. So let's call these ones A, B, and C. Okay, so how do I now know which peak is which? Well, the first thing, of course, later, next class, I will give you a table with characteristic chemical shifts for different groups, right? So if you're an NMR expert, you're like, oh yeah, methyl group should be at 2 ppm. So already based on that, but there's another interesting thing in NMR, and that's the area, that's the area under this peak. Okay, so if I take the area here, and the area here, and in the NMR world, people draw this like this. It's a bit strange, but welcome to the club. It's like this, right? And they will write the value of the integral under the peak. So you will see, and of course I didn't leave enough space, so I need to move this a bit down. So the integral, the area here will be 3, 2, and 5. Right, so the peak area under the peak, which is the integral, you can set it to the number of equivalent protons. It's clear or not? So the chemical shift depends on the chemical environment. So you have to first look which protons feel the same chemical environment, which is basically a symmetry argument, right? So I can look here. Then you can integrate the area under the peak, and that is proportional to the number of protons that have this same chemical shift. Question.
Why did this one has an integral 3 and
No, 5. Okay. So some peaks, so a methyl group will be narrower and therefore higher. So it's not about that's the important thing. It's not about the
peaks has the same larger for
no. So yeah, okay. In my drawing, yes, but in the real world, no. So some groups like methyl groups, they will have a narrower, sharper, higher peak than a benzylic proton or something. But it's about the integral under the. Usually, the highest peak is also has the highest integral also. But in this case, that's why I draw it like that. It's about the area. Okay, here I didn't draw it very to scale, but okay. So that's the area under the peaks. Okay, so that's very important, the integrals. Okay, then I already said this. There's characteristic chemical shifts. Okay. Go with my axis again. So different functional groups will have different characteristic ppms. For example, acids would be here. You can have aldehydes here. Okay. Benzylic ones, they will be somewhere here. Okay. Just quickly do this. So already by looking at the chemical shift, I can have some idea of what kind of proton I'm looking at. So X can be, for example, fluoride, chloride, bromide, iodide, oxygen, NO2. And 2 to 0. Okay. So I'll give you a larger tables and more rules in the next class, but basically the chemical shift already tells you something about what kind of protons they are. Then the area gives you how many protons there are. And then there's a last but very important effect, which is called spin-spin splitting, or the N+1 rule. Okay, so how does this go? It says each proton senses the number of equivalent protons, let's call it N, on the neighboring carbon atom. Okay, this is very strange, but very cool. You will see why. So if I have one neighbor, I will get N is 1 plus 1 is 2. I will get 2 peaks. And that is called a doublet. If I have 2 neighbors, I get 3 peaks. I get a triplet. 3 neighbors, I get 4 peaks. Quartet. 4 neighbors. Okay, we keep continuing. Quintet. You know, quintet, sextet, septet, octet, nonet, whatever. I mean, whatever. At some point, people just call it multiplet. So when you really don't know what's going on, you just say, people say multiplet. Multiplet means a whole forest of peaks and you really don't know what it is. Then you call it a multiplet. That's what you do in NMR. Okay. So, okay, last weird thing, and then we go to examples. So the intensity of these peaks, you can predict them using Pascal's triangle. Densities follow Pascal's triangle. It's a mathematical concept. It's quite easy, okay? You draw a triangle. Okay, we'll try to make it nice. And I put a 1 in the middle. So if I have 1 peak, I have a singlet, which is 1 peak, right? Like this. And in the spectrum, people often write with 1 letter S, singlet. Now, if I have 2 signals, I have a doublet with intensity 1 to 1. So I get this doublet. Okay, now in Pascal's triangle, the next row is 1, 2, 1. So all the sides are 1s. And then the other ones are the sum of the previous middle ones. So 1 plus 1 is 2, right? 1 plus 1 is 2. You already knew that. Triplet. So a triplet has intensity 1 to 2 to 1, which is 1 to 2 to 1. triplet. Okay, there we go. Quartet. Who's going to help me with the quartet? Quartet. Higher mathematics people. 1 plus 2 is 3. 2 plus 1 is 3 also, and 1. Okay, so quartet, I have 1, 3, 3, 1. Q. Okay, last one. This continues forever. Huh? So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and 1. So quintet will be 1, 4, 6, 4, 1. Okay. Quintet. Okay. Sorry, I have to hurry up. Okay, let's take an example. Chlorine, CCl, Cl, HA, H2B. An axis gone. Okay, so tell me, what are we going to see? So I'll give you the chemical shift. So this, the red one will have a chemical shift around 6. And the blue one will have a chemical shift around 4. But what's the shape? Okay, so the red one, how many neighbors does it have? The red ones have these ones as neighbors. We have 2 protons. So we have 2 plus 1 triplet. Right, so the red ones will give a triplet with an integral of 1. Nice. A. Okay, so I just look this proton, H, is connected to this carbon. I look what's the neighboring carbon. That's this one. The other ones are chlorines. Chlorines don't count. So I look at the next carbon and I look how many protons are there on this carbon. There's H2, so that's 2 protons. And then the rule is n plus 1, so 2 neighbors plus 1 will give a triplet. If there was an oxygen, nothing. No. No. Okay, and the blue, so let's go for the blue one. So for the blue one, we're now looking at this carbon, this neighbor. We have 1 neighbor, plus 1, we have a doublet. So this one will give a doublet here with an integral of 2. Right, so I can look at the chemical shift, I can look at the splitting, and then I know, oh, there must be so many neighbors or so many neighbors. Okay. Let's do one more example. We have this molecule, iodine, carbon, carbon, and we have 2 protons here, and we have CH3 here. Okay. So what are we going to see? So this one, how many neighbors? 3 neighbors. So it's going to give a quartet, right? 3 plus 1 quartet. So this will give a quartet around 3 ppm, which you don't know, but okay. Quartet, the integral will be 2. right? This one has two neighbors, 2 plus 1, triplet. Triplet around 2. And the integral will be 3. Okay? Okay. So last thing, coupling constant J. So the distance between those splittings. So let's draw a quartet. I'm going to draw these ones a little bit larger, okay? So if I have a quartet, I have a uniform distance between those peaks. And that distance is called J. And it's typically 7.5 hertz. Okay, we'll see what it does. Let's draw the triplet. Again, this distance will be J, which is the coupling constant. Then there's one other thing, which is really funny, is if you look carefully at this quartet, okay, this is drawn by hand, so you have to believe me. You see that it's not entirely symmetric. It's leaning a little bit, right? So the blue ones, this is the same molecule, this is this molecule, right? So the triplets and the quartets or any multiplet can be skewed, which means like hanging to the left or to the right, in the direction of the proton it couples with, right? So here we saw that this one is, let's say, downfield. So at higher ppms, this one is called downfield, and more to the right is called upfield. So if you are more, these two are next to each other, the red ones split because of the blue ones split because of the red ones. So they will skew towards each other. So if you draw little arrows, this one will point to the signal that corresponds to the protons that it's splitting with. Sorry, this after 2 hours, you're like, okay, what is this? Okay, we'll get back to this. Okay, so the last, so just to give you an idea of some numbers, right? So if I have a carbon-carbon, let's say 2 protons like this, the splitting constant, J, is 6 to 8 hertz. This number, 3J, why is it 3J, not 2J, not 4J, is the number of bonds involved. Okay, so I have 1, 2, 3. 3 bonds, 3J. Okay, this is just NMR, blah, blah, but okay, if you see 3J, it's because of that. So if we have a proton here and CH here, then 3J will be 4 to 10 hertz. And this one is funny. So if you have cis or trans protons, this one is 11 to 18 hertz. And this one is 6 to 15 hertz. Okay, so we're going to finish with that. So NMR, okay, we talked about all the how it works, the fundamentals. But if you look at the spectrum, the chemical shift tells you something. The shape of the peak, you know, singlet, doublet, triplet, quartet, is the multiplet, is it skewed left or right or not? And what's the distance between the splitting? All of these things give you information on what the protons in the molecule are.